You know, your smartphone, the internet, AI, pretty much everything we call modern technology can be traced back to the ideas in a single, super dense academic paper from 1936. So let's pull apart this foundational document and see exactly how one person's abstract thought experiment became the blueprint for, well, our entire digital world.
So back in the early 20th century, this was one of the biggest, most fundamental questions in all of mathematics. It sounds simple, right? But it really gets to the very heart of what logic and reason can even do. Was it possible for humanity, with enough time and paper, to come up with a perfect, universal method, an algorithm, that could solve any problem you throw at it with a simple yes or no?
And then, this paper lands. It's from a 24-year-old Cambridge mathematician named Alan Turing. He set out to answer that massive question, and his final answer? A resounding no. But the way he got to that no, well, that's what changed everything. He basically had to invent the idea of a computer just to prove his point.
Okay, let's give it its proper name. The problem Turing was tackling was called the Entscheidungsproblem, which is German for the decision problem. It was famously posed by the great mathematician David Hilbert. Now, Hilbert was an optimist. He truly believed a universal problem-solving method like this was possible. Turing, well, he was about to challenge that whole idea.
And this, right here, is where you see the sheer genius of Turing's approach. He realized, hang on, you can't prove whether a universal method exists if you don't have a rock-solid mathematical definition of what a method even is. I mean, what does it actually mean to calculate something? What are the absolute, most basic steps of any computation?
So this brings us to the very core of his paper. To define computation, Turing came up with this amazing thought experiment, a totally abstract, minimalist machine. And it was designed to do one thing, mimic exactly what a human mathematician does when they're sitting there calculating.
And he says it himself right here in the paper. He's not talking about gears and wires and electricity. Nope, he's thinking about the process of thought itself. He's breaking down the very act of human computation into its simplest, most fundamental parts. Let's take a look at what those parts are.
First up, the machine needs memory. For Turing, this was just a simple, infinitely long tape of paper, kind of like a roll of ticker tape. It's divided into squares, and each square can hold a piece of information. This is the machine's workspace and its memory. You can totally think of it as the great-great-grandfather of your computer's RAM.
Okay, so what do you put on this paper tape? Symbols. This is the machine's alphabet. It could be as simple as just a 0 and a 1, or maybe a few other markers. The key thing is there's a limited, predefined set of them. This is the raw data, the basic language of the machine.
Now for a really crucial idea. The machine has a state of mind. Turing actually called it an M configuration, but it's way easier to just think of it as the machine's immediate focus. Is it in the I'm adding numbers now state, or maybe the I'm looking for the next symbol state? It can only be in one of these simple states at any given moment.
And finally, how does it decide what to do? With a simple little instruction table. That's it. The machine just looks at its current state, and it looks at the symbol on the tape it's currently reading. That combination points to one specific instruction in the table, which tells it exactly what to do next. Maybe write a new symbol, move the tape left or right, and then change to a new state. That's the whole shebang. That is the entire engine of computation.
And look, this isn't just some modern interpretation we're putting on it. It's right here in Turing's original text. You can see him talking about M configurations, the tape, squares, and symbols. He's literally building this entire logical concept from the ground up, right here on the page. It's amazing.
So let's make this real for a second. Here's a super simple machine from the paper that's designed to do just one thing, print the sequence 0, 1, 0, 1 forever. Just look at the table. If it's in state B and it sees a blank square, the rule says print a 0, move right, and change to state C. Now it's in state C, so it prints a 1, moves right, and eventually it loops back to state B to start all over again. Simple rules, a totally predictable outcome. Turing argued that any computable task, no matter how complex, can be broken down into a table just like this.
Okay, so you could have a different machine for every problem, right? One for adding, one for sorting, one for printing 0, 1, 0, 1. That's powerful, sure, but it's also really inefficient. But then Turing had his next truly mind-blowing insight, and honestly, this is the one that really did build the modern world. This led Turing to ask a totally revolutionary question. What if the instructions themselves, that table of rules, what if that could be treated as just another piece of data? And this, right here, this is where things get truly wild. This is the birth of software. Turing showed that you could take any instruction table, no matter how complicated it was, and translate it into a unique string of symbols, basically just a single really long number. He called it a description number. Think about that for a second. Every possible program can be represented as a unique number. It's just a piece of data. This is literally the ancestor of the app icon you tap on your phone.
And this leads to his masterstroke, the idea of a universal computing machine. Instead of building thousands of different physical machines, you could build just one. You would feed it the description number, the program, for whatever task you wanted to do. The universal machine would read this program from the tape and then perfectly simulate the behavior of the machine it described. This is your laptop. It's one piece of hardware that can run countless different pieces of software. It's an incredible idea.
So now Turing has his tool. He's got a perfect mathematical definition of what computation is. He can finally circle back and attack that original question, the decision problem. He's ready to find out what the limits of logic really are.
Okay, so let's frame the final challenge. Since every program is really just a number, you can imagine making a huge list of every single possible program that could ever exist. Now for the ultimate question. Could you write a master program, let's call it a halting checker, that can look at any other program from that list and its input and tell you with 100% certainty if that program will eventually finish its job and halt, or if it's going to get stuck in an infinite loop and just run forever?
This is the ultimate decision problem. If you can solve this, you can solve the Entscheidungsproblem. And Turing's answer, it was absolutely stunning.
It can't be done. It's impossible. A master program like that, a perfect halting checker, is logically impossible to create.
He proved it with this beautiful proof by contradiction. Imagine you create a mischievous little program, and its only job is to ask the halting checker, hey, am I going to halt? Now, if the checker says, yep, you're going to halt, the program's code immediately tells it to enter an infinite loop. But if the checker says, nope, you're going to loop forever, the program immediately halts. See the problem? No matter what the checker says, it's proven wrong. This logical paradox means the perfect halting checker itself cannot possibly exist.
And that's why this matters so much. By trying to solve this abstract puzzle in pure mathematics, Turing proved that there are absolute unbreakable limits to computation. Some perfectly well-defined problems are simply not solvable by any computer ever. And in the process of proving that, he gave us the universal machine, he gave us software, and he laid the theoretical bedrock for all of computer science, all in one go.
So we end with this thought. Turing defined a computer by modeling a human mind doing math. If he then proved that this idealized machine has fundamental built-in limits to what it can ever know, what does that imply about the ultimate limits of our own systematic, logical knowledge? It's a question that started on paper in 1936, and it's one we are absolutely still grappling with today.